We now take on the topic of acids and bases. So I would like to begin with a definition, but that's actually not trivially easy in this case because there are actually several definitions of acids and bases that have come about over the years. But a good starting point is the Arrhenius definition, which was developed in the late 1800s by Svante Arrhenius. And his definition was that an acid is a compound that contains hydrogen and ionizes to produce H plus in water. Okay, so an example of the ionization of an acid is taking HCl and having it break apart to give H plus and Cl minus. Arrhenius's definition of a base is a compound that ionizes to produce OH minus in water. Okay, so the classic example of a base is sodium hydroxide, NaOH, ionizing to produce Na plus and OH minus. Okay, and for this course, for first semester general chemistry, this definition will actually be fine, but it does have its limitations that'll become more apparent to you both in the second semester and especially in organic chemistry. So just briefly, those limitations are that the Arrhenius definition is specific to one particular solvent, water. The definitions say in water. And we now know that there are plenty of compounds that are acidic or basic in solvents other than water. Secondly, not everything that's generally considered a base actually produces hydroxide ions. Okay, there are bases that don't contain hydroxide. And then thirdly, we've come to know that the key process in an acid-base reaction is actually the transfer of a proton. So protons are really important in acid-base chemistry. Hydroxide, not so much so. They just happen to be what happens when certain acid-base reactions take place in water. So the more general definition of an acid and a base were actually developed by Bronsted and Lowry a few years later. And Bronsted and Lowry have defined an acid as being a proton donor and a base as being a proton acceptor. So in the world of Bronsted and Lowry, an acid is just not going to spontaneously dissociate to give H plus and Cl minus. In the world of Bronsted and Lowry, HCl is going to react with the water. It's actually going to do an acid-base reaction with the water. We'll get to that more in the next lesson to give H3O plus and Cl minus. And in this case, HCl is the Bronsted acid and water is the Bronsted base. So what you are definitely going to have to be able to do in this course is recognize acids. And I like to think of acids as falling into three classes. So the first class of acid are binary acids, which means they have just two atoms in a molecule. So they're diatomic molecules containing hydrogen and a halogen. Okay, so the four examples that are important are HF, hydrofluoric acid, HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. The second class of acids are what I call the inorganic oxyacids, and they have a general structure where A is a central atom. It's going to be a nonmetal. It is doubly bonded to some number of oxygens, and it has some number of OH groups on it. So this is best illustrated with some examples. So one example is nitric acid, where the central atom is nitrogen. It's doubly bonded to one oxygen and has one OH. Sulfuric acid, H2SO4, central atom is sulfur. Two doubly bonded oxygens and two OHs. Phosphoric acid, H3PO4, one doubly bonded oxygen, three OHs. Carbonic acid, H2CO3, one doubly bonded oxygen, two OHs. Perchloric acid, HClO4, three doubly bonded oxygens to chlorine as the central atom, and one OH. But what's common about all of these is they've all got at least three oxygens in their structure, and at least one of them is doubly bonded, and at least one is an OH. Then we have the organic acids, and they have the general structure RCOOH, where R is either carbon or hydrogen. So there are many, 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 many organic acids. They're also called carboxylic acids, and you'll learn about those in much more detail in an organic chemistry course. But just to give you a few that show up in this course, acetic acid. And notice I've given two formulas for acetic acid. I've given CH3COOH, which is the way I always think about them, but then also HC2H3O2. Writing the formula out that way is indicative of the fact that there is one acidic hydrogen atom, and then there's everything else. So when you dissociate it, it's going to make H plus C2H3O2 minus. Lactic acid, okay, HC3H5O3. It has another OH on the carbon next to the one containing the C double bond O, but that one is not acidic. It's just the OH that's on a carbon with a C double bond O that's acidic. Oxalic acid has two C double bond O's, two OHs, and two acidic hydrogens. And when it loses its hydrogens, it makes the oxalate ion, which is one of the polyatomic ions that you were introduced to. And then finally, another important acid is citric acid. This has got a much more complicated structure. I don't expect you to know this structure. We're up to 6 carbons, 8 hydrogens, and 7 oxygens. So that's a particularly large molecule. But if you look carefully, it's got 3 of these COOH groups. So it actually can lose 3 hydrogens in acid-base reactions. Okay, so I like to introduce you early in your chemistry career to chemical structures because I always think about compounds in terms of their structures, and I think that's a very good way for anybody studying chemistry to start thinking about compounds. Okay, our next topic is that of strong and weak acids. So strong acids, by definition, dissociate 100%. They completely become H plus and A minus, whatever the anion that would be produced is. So they're going to be strong electrolytes. Remember that electrolytes are compounds that conduct electricity. Strong electrolytes conduct lots of electricity because they generate lots of ions in solution. Okay, so there are 6 strong acids that you're going to need to memorize. I know I hate telling students that they have to memorize things, but there are a few things in this course that you need to memorize. Hydrochloric, hydrobromic, hydroiodic. So 3 of the 4 binary acids. Sulfuric, perchloric, and nitric. Those are the 6 strong acids. Okay, and I'll just give you a couple dissociation reactions that you haven't seen yet. So again, I'm writing these out in kind of the Bronsted-Lowry format. So H2SO4 plus H2O gives H3O plus and HSO4 minus. So one of the protons has been transferred from the sulfuric acid to the water. And then similarly with nitric acid reacting with water, still gives H3O plus, okay? Every strong acid, when you put it into water, is going to give H3O plus. And now you have nitrate, NO3 minus, as the species that's left. Okay, so then all other acids on the previous slide, including HF, are weak acids. Weak acids only dissociate to a small extent. And when I say to a small extent, I mean less than 1%. And in some cases, much, much less than 1%. Weak acids are going to be weak electrolytes. There are some ions in solution, so they conduct the electricity a little bit, but most of the acid molecules are still neutral, and therefore you're not going to get much conduction of electricity. Okay, so an example of a weak acid dissociating when you put it into water, acetic acid plus H2O. 99% of that acetic acid, greater than 99%, in fact, much, much greater than 99% of that acetic acid remains unchanged and simply becomes an aqueous solution, acetic acid dissolved in water. it generates a small amount, much less than 1% of H3O plus and a small amount of CH3COO minus. And you will calculate in second semester exactly how much H3O plus is generated in this reaction. And from that, you would actually be able to calculate what the pH of a solution containing acetic acid is. So that's coming up in second semester. We can do the same analysis for bases. So the strong bases that you're going to encounter in this class are metal hydroxides, especially involving the group 1 and group 2 metals. So sodium hydroxide, potassium hydroxide, lithium hydroxide, and then also magnesium, calcium, strontium, or barium. Note that if it's a group 2 metal, there are 2 OHs because group 2 elements want to form a +2 charge. And you'll learn about more strong bases in your organic chemistry class, but this will be good enough for this class. So the dissociation reaction of a strong base, NaOH becomes Na plus and OH minus. So we actually saw that on the first slide. The strong bases are all already ionic compounds. So just treat them like any other ionic compound. They're going to dissociate 100%. But never try to break the OH bond in a hydroxide because hydroxide is a polyatomic ion and the polyatomic ion has to stay intact. Weak bases do not contain the hydroxide ion, so there's not going to be an OH in the formula. But what they will actually do is they will accept a proton from water, and then the hydroxide is generated because that's what's left over after the water donates a proton. So the most important example of a weak base for this course is ammonia, which has the chemical formula NH3. Ammonia is actually a gas. So if you take gaseous ammonia and dissolve it in liquid water, what you get, greater than 99% again of that ammonia stays NH3 and just becomes an aqueous solution. But a small amount of it is going to accept a hydrogen from H2O. So that H2O will actually do the dissociation. In this case, water is behaving as a Bronsted acid. It does the dissociation to a small extent, less than 1%, gives its proton to NH3, that generates NH4 plus aqueous, and then any water molecule that lost a proton, the OH minus is what's left over, again, less than 1%. But the presence of that OH minus in solution, the hydroxide ion, is what makes the solution basic. Okay, one final thought in this lesson. I know this has been a long lesson, but I want to kind of put together on one slide some thoughts about compounds with OH bonds. Because we've encountered a variety of such compounds in this lesson. Some are acidic, some are basic, and some are neutral. Okay, the acidic ones are the inorganic oxyacids and the organic acids. Note the OH bonds in the structure. The basic ones are sodium hydroxide, contains an OH bond. And remember that hydroxide is a polyatomic ion and must remain intact. Then there are also neutral compounds that contain OH bonds. We haven't met them yet in this lesson, but an important example of neutral compounds with an OH bond are alcohols, such as ethanol, CH3CH2OH. And what makes an alcohol is that it contains an organic group, that's going to be CH3CH2, also known as an R group, covalently bound to the oxygen, and there is no CO double bond next to the OH. Okay, so here's what you have to remember to keep this straight. Once you have identified a compound as being acidic, it's going to dissociate, and in the course of dissociating, it will break the OH bond. Basic compounds will dissociate, but when they dissociate, they will not break the OH bond because hydroxide is a polyatomic ion and must remain intact. And finally, neutral compounds such as alcohols will not dissociate. They will just dissolve in water. And in fact, they will not dissociate unless they are reacted with a strong base. Okay, so that's, I know, as I said, that was a long lesson, but that's our introduction to acids and bases. And then in the next lesson, we'll talk about the reactions that acids and bases undergo with each other.